Hello and welcome back to MAPP 3D assignment number 5, video 5. And this is for the Speaker Systems Design and Optimization course at New England School of Communications at Husson University. So moving on, we're going to dive into the heart of this assignment and get the work on the front fills, getting them time aligned. We're going to start with the inner front fill, and we're going to use the ReLEPT method to get it level time and polarity combined. So let's switch to the measurement mute. Let's go off and get ready to take a trace of the mains only. So I think the easiest thing to do is go off to compass and make sure the right mains are muted, but the left mains are not. So I'm going to turn off the link there, and well, these want to stay muted. Actually, I want to do the opposite. I want to unmute those. And I'm going to keep the front fills muted because we're going to just listen to the mains first. And let's go over to MAPP 3D and look at the model view, and we'll do a prediction here. We should see the left mains only, and that's indeed what we're seeing. And let's go over to measurement view, and we can see the magnitude trace and the impulse response and the phase trace. We want to make sure we're going to be doing we're going to be aligning the in front fill, the front fill in first. So we want to make sure you select the front fill in mic. And the next thing you do is press the auto button here. This will bring the transient to the center. This is basically the delay finder in SMART, and that'll clear up the phase trace, so give you a slightly better data there, and put the transient in the middle, aligns it on the 0 milliseconds, and it's putting in the propagation delay here of 24.49 milliseconds. So that's the first part, getting kind of set up to go. And let's take a trace of the house mains. This is the house mains right now, so this is the store trace button here, so do that, store trace. This trace, we're going to call it mains house left at front fill in mic. So you know what it is and where it was, and we'll save it. And notice that it has put it down here in this stored trace location, and you can click the little eyeball icon and make it visible, and now the two are overlapping, so the pink and blue kind of make, the red and blue kind of make this pink color here. And good, you're all set up, and that looks pretty similar to what we have. Same thing here. And next step on the agenda, we'll go to compass, and we're going to mute the mains and open up the front fill inner mic. So we'll go to compass. It's easiest to do that via compass. So mute the mains and open up the front fill inner. So only the front fill inner. And I think it's a wise idea whenever you're doing this and you're using compass is to just double check, make sure it works. The command you've just sent it is indeed working. And we do have the front fill inner. Now, other things were selected. Let me try that one more time here. So we've got that front fill inner. That's great. Now let's look at the measurement view for that only. And now we see two very different signals. And let's concern ourselves with, well, it's the ReLEPT method, right? So what are the steps in the ReLEPT method? I want to see what the instructions tell me here about this. The first step is really to get frequency response to match. You want the response of that front fill to match the response of the mains. And I'm talking about frequency response in this particular case. And so what you would do in the real world to achieve this is probably take and have all the main, have at least one side of the mains on, have multiple microphones, measure and kind of build an average response magnitude trace of what the PA sounds like across the space. And then you can use that as a guide for how you're going to EQ the front fill. Now, this is very difficult, if not outright impossible to do in virtual. I'm not aware of how to set up an easy way to set up multiple microphones and average them together to come up with a trace. And the other thing is this virtual doesn't do anything about the actual room acoustics and the reflections off the walls and ceiling and floor and all that. So we're going to skip that part of the response trace. But we can put in the high pass filter in the front fills if we choose to. You can see that there's quite a lot of, and I'm going to expand the response amplitude trace here, make it bigger. That's what this button does here, make it bigger. And you can see, yes, the front fill is quite a bit louder. The blue one is the front fill at the mic position, and the red one, the off-axis mains, is pretty jagged in the HF and lower in level. But you can definitely see that there is enough. There's going to be enough level. Once we bring this blue trace down, we're going to see that there's going to be enough bass energy coming from the mains and probably the subs. We can probably high pass out this information in the front fills. So let's do that. Let's do maybe around 250 hertz in a second order filter, something like that. So let's go to Compass and front fill inner and open up the processing page, if you will, and let's engage the high pass filter and bring it up from 40. Let's try 250 hertz. And you've got a couple different choices, or a bunch of different choices here. You've got the second order legacy. That's like what you would find in the Galileo processor, and that will work. Or you can go with a more predictable standard Butterworth 12 if you want. And so let's go for that. And of course, if I go back to overview, I should see that filter there. And I should also see that filter in Map 3D on the processor page. There's the filter. And now we see the effects of the high pass filter on the front fill. So that should help out a little bit and kind of keep the front fill from combing with this energy coming off the mains. And of course, we don't even have the subs on, so the subs would be producing down there anyway. I think the real mains would actually be high passing there slightly because that area would be left for the subs instead. Okay, moving onward. The next step after high pass filtering is to get the level more similar. And we were just on that window. And you can really see that, and I already mentioned that the level. So let's bring it down. And about how much? Now you can adjust these parameters here. This one. You can set up your deviation per grid mark. That's 10 dB per grid there. And you can also kind of zoom in, if you will, about how far down it's going to go. What's the full dynamic range that this spans on the y-axis. So I don't know, let's go to 30 dB. That's going to be hard to read. So let's make it 60. And you can see it's about 10 dB-ish because it's about one grid mark here. So let's turn this in front fill down by 10 dB in Compass. That's pretty easy to do. Just type in -10 here. Oops, I typed in the wrong thing. And now we will go over to Map 3D and have to repredict. And that's about right. Now, I know this is really jagged. You're off axis. You're below and slightly behind the main hang here. If you smooth a little bit, it might look a little bit more consistent. And I would say maybe we're just a hair low now, below average. It's hard to say what average really is. I mean, maybe that's right. I mean, do you want to do -9 instead? I don't know. This may be slightly different than what I did with the instructions, but does that look any better? No, I'll go back to -10. So we'll go with that. So, and predict. And there you go. So we've kind of equal level in the upper frequencies there, which is what we want at that particular acoustic crossover in front of the inner microphone. So going back to the instructions, it's right. I think we're ready for time aligning, and which in the relept process, that's the P and T at the end, polarity and time. So to do that, let's shrink the result amplitude window back to normal size, and instead we'll expand the IFFT window, or the impulse response window, and you can definitely see blue here is arriving earlier. How early? Well, changing the resolution here under third octave smoothing, let's bring it down to 70 milliseconds. It zooms in a little bit. And you can see it's, I don't know, 15, 17 milliseconds early. So what's nice here is that MAPP provides this metric over here, peak impulse, parentheses relative. And this metric, which is currently showing minus 14.11 milliseconds. This indicates the distance in milliseconds between the peak of audio that it's currently seeing, which is this front fills here, and the center of the window, the 0 milliseconds time. And of course, the 0 milliseconds time, earlier you set auto, the delay finder, to set this 0 to calibrate to where the mains arrive in time. So this red here, of course, is the mains, and you can now extrapolate that because the distance from here to here, from the front fills to the mains, is shown by the peak impulse relative. That value, minus 1411, is the value we want to put in to the processor and delay the fills by. So 1411, if we go to Canvas and type that in, Compass, and type that in, front fill delay it by 14.11, boom, and we will predict here. You can see they're right on top of each other. And you can zoom in even more with this down here. You can move down to a 7 millisecond window, and you can still see they are right on top of each other. So that's cool. They're in time. Now, zooming out here, you could still spend some time looking at the phase trace, and you do see that there is this phase wrapping here at 125 hertz. You're 180 degrees out of phase, where the mains wrap at 63. And maybe that bugs you a little bit, and that's actually the effect of the high-pass filter. If I turn off the high-pass filter, we should see a lot of that go away. See? Phase wrapping is closer. But you want that high-pass filter. So it's a little bit of a trade-off. High-pass filters are going to add phase shift, but they're also going to reduce the frequencies that you're having other phase issues with. So it is kind of the way it needs to be. So anyway, we are in level in time. Polarity is pretty obvious. I think these are in polarity. If they weren't in polarity, and let's reverse the polarity on this for a second and show you what that looks like. We reversed the polarity on that front fill and did a prediction. You could see that the transient would be inverted here as well, and that tells you right away that the polarity of those two sources was together. So I think we've pretty much aligned this, which is pretty nice. And we're good. Let's see if the instructions add anything else to say. Nope. We kind of did that. Oh, I got a typo there. It needs to be made into 2 words. So at this point, let's capture a trace of this finalized, adjusted front fill. And the name I want you to name that trace is front fill in at house left. Cool. So we will store that. So store live trace, and we'll put that in there, and we've got it adjusted. So that's kind of cool. It's there. You're not going to need to look at it. And at this point, I would save map as a new version. Save project as. So I'm going to add an 05 to this. And I would also wisely go to Compass and add a new snapshot. Create new. So front fill inner aligned. And we will save the project as well. All right. And so I'll catch you in a moment on another video. Oh, one last thing. I'm sorry. For the assignment, I want you to take a screenshot of this aligned screen. And the screenshot is going to be named front fill house left inner aligned. Your name. So I'm going to copy that. So take a big old screenshot of this window and do it of the whole screen so I can see everything in your window, so I can really know what's going on here, and then name that screenshot what the instructions tell you to. Okay? Cool. Catch you on the next video where we will do the other front fill. Bye-bye.